Okay, so maybe we get started, and till I spend a few minutes to introduce you, I'm sure more people will join. So it's our distinct pleasure today to host Professor Panagiotis Tsiotras from Georgia Tech. Um, Professor Tsiotras got his degrees from, I know the PhD was finally from University of Purdue, or you worked there? That was your first position. Now, I remember you came to Georgia Tech from Purdue, right?
I came from Virginia Tech. University of Virginia, actually. I got my degree at
University
Purdue.
of
I
Virginia.
was assistant professor for 4 years at University of Virginia. Yeah.
Oh, okay. And his work has been recognized by a number of awards, including IEEE Control System Society Excellence for Aerospace Controls. He's fellow of IEEE and the AIAA, and he's kind of a well-recognized expert in control, machine learning, with applications to space robotics and many other industries like self-driving cars and others. So with that, I'll let you take the stage, and the recording is on. And it's
Okay.
all yours now.
All right. Thank you very much. Thank you, Naira. Thanks for attending this virtual seminar. So this is going to be about the work that we have been doing in my lab for several years now, probably close to 10 years now, on covariance steering. And maybe some of you have heard about the term, maybe some of them haven't. I'll try to explain, and you'll see. My presentation is kind of split in two. I'm going to give you a little bit of theory, and then I'll focus on a couple of results. Some of them are from control, some of them from robotics, and more recently from generative AI, to demonstrate how flexible and versatile this approach is. But let's start with oops. Okay, let's start with an example that maybe will be relevant or interesting, I guess, to most of you, since this is a ULI on most people, I guess, they're working on this ULI on flying vehicles. So let's say I have this taxi was to land on top of this building. All right, but there are winds, right? So there will be disturbances. So there is no one particular trajectory this thing is going to follow. There's going to be a bunch of different trajectories, possible trajectories, or different realizations. In addition to that, you want to guarantee that maybe you remain in some cone of confidence. This is maybe safety cone of constraint, of some sort of constraint, or maybe some kind of field of view, whatever. But regardless what the particular realization is, your objective is to hit that particular area at the end of your landing trajectory. Similarly, you may have another example. You may have an aircraft trying to land on a runway. Again, there may be different disturbances and winds and stuff like that. So the vehicle is not going to follow one trajectory. There are many potential futures. So there are many different realizations, but you want to, at the end of the day, to hit at the covariance, or hit some area at the end of the landing. And then you can have this cone type of constraints or some other constraints. And you can think more similar examples. Maybe you want to do package delivery. You throw things and you want to make sure that these things are landing in a particular area. So what all these problems have in common, these are finite time problems in which you want to control the state, the dispersion of the states at the end of the horizon, perhaps due to some constraints, state constraints and control constraints. So that's the problem. So at least from a practical point of view, theoretically, essentially, you have a problem that looks like this. You have a bunch of initial states, or you can think of it as a distribution, or maybe some covariance that give you a little bit an idea about how the states are distributed at time zero. Then you have some target distribution, some target covariance at time t is given, and your objective is to find a controller that no matter where you are at the beginning, maybe some distribution Gaussian, who knows, with some x0 mean and some sigma 0 covariance to hit a particular mean and covariance at the end. So you want to do that for all trajectories, find a controller that will do that for all trajectories. All right, so that's the problem. Of course, if you set it up like this, the first question one may ask, is that a well-posed problem? Is that even possible to solve this problem? Turns out that the first time somebody tried to address this problem in terms of the controllability question, whether this is indeed a well-posed problem, it is this nice paper by Brockett, who around 2012, I believe, or maybe a little bit earlier, he published this paper that basically showed that this is indeed possible. And he gave the first controllability result that says that if you're given a linear system, this is a continuous time. Maybe you can see my cursor. Let me see if I can see if you can. Okay, my laser pointer. So this is a continuous time, but similar results hold for the discrete time. Basically, it says that if you have a linear system and you have this control law have a gain K, all right, and they have some feed-forward V. And if you write the equation for the covariance, it looks like this. It's a bilinear system because now if sigma is your state, you have kappa times sigma. Kappa is the control for the covariance, as you can see here. So the question is, can you control this equation, right, from some sigma 0 to some sigma E? And the answer was positive. He said that, yes, you can do it. And the condition, surprisingly or not, is that AB is controllable. So it's exactly the same condition you have for the first moment, right? So nothing. So this is good. I mean, no extra condition in terms of controllability. If the system controllable, then you should be able to, with a K, find a K matrix that will steer the covariance from any positive definite to any positive definite at any time. So this is good. So after that, there is a result that generated some interest on this problem. And the first problem that actually coined the term covariance steering, as far as I'm concerned, it was this paper, or like a sequence of two papers actually, by Trifon Georgiou and his former student Yongxin Chen. Now he's a colleague of mine here at Georgia Tech, and then Michel Pavon, a physicist from Italy. So basically, they looked at the problem of if you have a stochastic system of this form, then you have you have some noise here, and then you want to steer from some initial Gaussian distribution to some final Gaussian distribution with times t is fixed, and among all possible solutions, find the one that minimizes the energy cost. So that was the first paper, and actually a two-part paper, and they actually won the ACRL Outstanding Paper Award, which is in the transactions for this work. So now it turns out that this is not necessarily a new problem. There are many interesting connections with more classical problems in control and mathematics, and this has to do with the optimal mass transfer. Moving or shaping a distribution, it's a fundamental problem that has been around for centuries. The first person who actually looked at this problem from a mathematical point of view, more formal point of view, was Monge. It's called the Monge problem, back in 1781, and he was interested in the problem if you want to move a pile of dirt from one place to the other. The total mass doesn't change. You just want to reshape it, to reform it, and you want to move the pile of dirt from one point to another, but you want to use as little effort as possible. So essentially, mathematically, this boils down to trying to minimize some integral of that form, where c is the cost. So every point x has to be transferred to some new point t of x. So you're looking for t, this map t, and the initial distribution is rho 0. Okay, so you want to minimize to find this t, this map t, that takes you from initial distribution rho 0 to a final distribution rho 1. And here t belongs to this set. This is just all the mappings that take the rho 0 to rho 1. This is just a push forward. So okay, it turns out that this problem, many people have been looking at it. It turns out not an easy problem to solve. Sometimes it does not have a solution. So about 1942, Kantorovich came with an interesting formulation of the problem, which is a function of relaxation. So instead of looking at the map T, which it was difficult, basically you're looking for a coupling pi between row 0 and row 1. So essentially, we're looking for a coupling with the right marginals. So this pi, think of it as sometimes called the coupling or the transport plan. It basically tells you who goes where, right, from the beginning to the end. So that is kind of well known. Another big breakthrough, and that's the connection that we're interested in, and that's the connection that actually motivated Trifon to work on this problem, is this seminal paper by Benamou-Brenier. Basically, they showed that this problem has a very strong connection with stochastic optimal control or optimal control. So this is basically this is equivalent, the Kantorovich problem is equivalent to solving this problem, right? So it's kind of, you have a dynamics now, right? But this is trivial dynamics, just integrator, and you want to move x0 is distributed according to row 0 and x1 distributed according to row 1. So if you solve this problem, basically you solve it. So there's a nice optimal control formulation for the optimal mass transport, at least for this version, and that generated a lot of interest in the community, where people start using control techniques to solve these types of problems. There is also another connection with another interesting problem, which is also been around for some time. This is the problem of so-called Schrödinger bridge. It was posed by Edwin Schrödinger in 1932, a physicist, and he looked at the he posed the following thought experiment. Basically, he said, if you have a bunch of particles at time t0 and you let them evolve, and then you observe what happened at after some time, let's say t equals 1, and then you think that this particle should be distributed or should follow some kind of Brownian motion. But then when you look at the distribution at the end, you see that the distribution is not what you expected, right? So there is some kind of surprise factor of what happened at the end, and then you say, okay, among the all possible paths that these particles, follow, what is the one that it is the most likely? That means it's mostly the one that should be closer to what I was expecting, which in this case, a Gaussian. A Wiener process. So the problem can be formulated in the path space as finding the path measure I that is as close as possible to some reference. Typically, that will be some Wiener process with the right marginals, because these are given. Empirically, I observe this. I just want to find pi, what is the actual paths that they were followed. And it turns out that this also has an interesting thermal control formulation. It's very similar to the previous one, Benamou-Brenier, but here you also have this extra term, this noise term that enters the system. Okay. These problems, Schrödinger bridge problems, have become very popular recently because they have been used a lot in the generative AI type of application. I'll show you the connection later on. So one more thing before I get to what I want to discuss today. There is also a version of the optimal transport. Optimal transport was this first term here. You can add this entropic term that measures the difference. By the way, I forgot to mention, KL is a Kullbaum divergent that measures how two distributions differ. It's kind of a distance, if you think about it. It's not exactly a distance, but think of it as a metric that measures how far away a distribution or a measure is from another one. So here, for example, how far away pi, the coupling, is from the rectangular, I would say, or square measure of the two marginals. So if you do this, so you put this entropic term, turns out that this is exactly the problem of Schrödinger bridge. So it solves exactly the Schrödinger bridge problem, this problem here. Okay, so this problem is equivalent to this problem. All right. Now, what is interesting is this result is what I'm going to use later on. Basically says the following, that we know very well how the Schrödinger bridge problem, what is the solution to the Schrödinger bridge problem. It has a very interesting solution. So it turns out that the solution to the Schrödinger bridge problem is actually a mixture of Brownian motion. Rho here is the flow of the process, okay? So how the density evolves in time, Okay, and basically it says that it is the average or the summation, yeah, the average of Brownian bridges. All right, so W is a Brownian bridge. This is a bridge that connects 2 points, x0 and x1. So you pin the process at x0 and x1, okay, and then you let it evolve like shown up here. Okay, so that's the Brownian bridge. And then you have different x0 and x1. x0 is taken from the initial distribution, x1 is taken from the final distribution, and you take the mix of all of them according to the optimal transport plan. And if you do that, this will give you the solution to the Schrödinger bridge. Will give you how the density will evolve. It's kind of very interesting result. Basically, it says that if you have a bunch of point-to-point solutions, and then you take the average of those according to the transport plan, then that solves the problem. So let me tell you a little bit what I'm going to do for the rest of the talk. I managed to waste the first, I guess, 17 minutes. Well, not waste, but give you a little bit of the background. But then I'm going to tell you a little bit about what we're doing in this area. So I'm going to give you a little bit of theory, and I'm going to tell you the basic idea or the basic theoretical result that we have been using. Then I'll give you a few examples, recent examples of how to do covariance steering using data-driven methods and the distributionally robust versions of that. And then hopefully I'll focus. I would like to focus a little bit more on the application. I'm guessing most of the audience will be interested in the applications. And I chose 3 areas: control, robotics, and generative AI, to show you how you may be able to use this type of techniques. All right, so let's look at a little bit of math. So here is the problem. I'm going to discuss the discrete version of the problems, the discrete times. There are equivalent versions for the continuous. There is a little bit of difference, not much. I think the discrete, in my opinion, is a little bit more clear. You don't have to use it with measures and things like that. But keep in mind that everything I say here, it's more or less there exist equivalent results in the continuous time. And if you're interested on those, at least most of them, that exist in the continuous time, you can look at the work at the Trifon and Yongshin Chan. All right, so we're given this problem. So the discrete problem, use a control W is the noise, and we're here's the problem. I'm given the x0 is distributed according to some Gaussian with mean mu0 and covariance sigma 0. And I would like, after n steps, that the final state, it is distributed according to some Gaussian with some mean and some covariance. So, okay. And then I'll give you also some cost to be minimized. This is a standard cost that you see in LQG. And you have this terminal term. In our case, we don't really need that term. So we're going to drop this term. The reason is that this term here essentially tells you a little bit about the dispersion, indirectly, the dispersion of the final state. But here I have a direct way of controlling it. So I don't really need that. Okay. And then, then the question is and I give you some initial covariance, some final covariance to solve this problem. Find the controller to solve this problem. All right, so that's the problem. The first things first. If you write down the equations, it turns out that the covariance steering problem is similar, but it's not identical. But it's similar to the LQG problem, to the LQ problem. In what sense is the LQ problem? Basically, you have Riccati equations and you have Lyapunov equations. So in this problem, turns out that you need to solve these 2 types of equations, the first equation and the second equation for P, this matrix P and this sigma is the covariance. But as you can see, although you have this coupled set of equations, the boundary conditions are atypical in the sense that both boundary conditions are in the sigma and the covariance and not in the pi. So it's not an initial value problem. You can say, oh, it's always exists a solution. So it's not really clear whether this system of equations has a solution. So in the first result that we prove, at least theoretical result in that paper, was published last year in Transactions, basically we show that indeed there is a solution, there is existence, and we showed that by showing the fact that the map from P0 to sigma n is a homeomorphism. Therefore, for every sigma n exists a unique P0. If you have P0 and sigma 0, then you can integrate forward. So there's no issue. And turns out actually that the optimal controller for this, it turns out to be of this affine form. Again, a priori, you don't know, you expect or you hope or you suspect that this is the case, but we prove rigorously that the optimal controller is indeed of this form. Okay. All right. So here's an example from the simulation that we start from some initial covariance. I think this is the initial covariance and this is the final covariance, a different realization. And you can see at the end, we hit exactly the covariance we want. So, I mean, it works. So how do we solve this problem? Since we know that the controller is affine, then we're looking for controllers of this form with some K and some V. V is the feed forward, K is the feedback. So you need to find these two. This parameterization based on the theorem I showed you before is general. It's as rich as you can. You don't have to look for more complicated things. So if you look for K and V, you solve the problem. If you write the equations, you get the first equation and the second equation. The first equation is for the mean, the second equation is for covariance. And you see some interesting decoupling here that the feed forward affects only the mean and the feedback affects only the covariance. All right, so if you want to control the dispersion of trajectories, you need to use feedback. You cannot use it just with feed forward control, which is of course known, but it's good to see it in plain equations like this. All right, so I need to solve this equation. The problem with the second equation, remember you have K times sigma, so it's not linear. You have a bilinear term here that destroys standard techniques. So you're going to do this transformation. I'm going to say U is my new variable, K times sigma, and then I'm going to substitute, and then you get this equation. By the way, I don't really care about the new equation or the mean because it's decoupled, so I'm just looking only at this equation here and the cost. So if you do this transformation, you get this term here. Okay, still is a little bit of problem. You have sigma inverse showing up in this equation where the covariance equation looks like this. So everything looks linear. Sigma enters linearly, U enters linearly, no problem. But you have this extra term that is annoying. So as usual, you're gonna do the trick of the slack variable. You introduce the slack variable, and then we're going to but then we're gonna substitute this, okay? And then turns out that the problem looks like this, but I substituted the equality with inequality, and therefore I can turn this to an LMI, and this is a relaxation, but it turns out to be lossless. This is the actually interesting fact. So you solve this problem, and essentially you can solve it to optimality. Okay. So that's the basic idea that so if you want to remember something out of this is that this problem can be solved in a convex manner. Okay. There are many extensions. We looked at the problem with chance constraints of that form. The probability that the X is in a hyperplane is large enough. So here's an example. It's a thing from a quadrotor that's flying in a box, so it doesn't leave this box, and you can see here the covariances. You can do output feedback, nonlinear covariance steering. We have some results on non-Gaussian disturbances by treating the problem a little bit differently. Instead of propagating the distribution, we propagate the characteristic equation. So this allows us to work with non-Gaussian distributions. We recently have a result that should appear recently about the controllability and reachability of the problem. I told you, for example, that if A and B are controllable, then okay, the system is controllable in terms of the covariance. But another question is, what if it's not controllable? Or what is the controllable space of all covariances, right? So that's an interesting question by itself. And then we characterize the controllability, reachability properties of the system in this paper. So if the system is not controllable, what is the set of the controllable invariances? Sorry, controllable covariances. So I have, I'm going to, I realize I'm behind schedule because I really like to go to the applications, but I'll give you the gist about two different versions of this problem. One is the data-driven approach. So we can use covariance steering if you don't know the matrices or you don't know the system. I think it turns out you can do that. Here, let me give you the case that we have no noise. So this discrete system is like this, but you don't know A and B. You still want to move the initial state from some initial Gaussian to some final Gaussian, but you don't know A and B, and you may have a cost here. So there are two ways of doing this problem. As usual, one is the indirect approach. That means that since you don't know A and B, based on the data that you collect, you find what A and B are, then you have this, let's say, estimated A and B matrices, and then you just use regular techniques. Or there is a direct approach that has become popular recently. The direct approach means that you don't have to construct A and B directly. Necessarily, you just solve the problem just from the data itself. This is based on, for those of you who are familiar with the theory on Williams' fundamental limits, it's been around for more than 30 years now, but people rediscover that result, and there see a lot of application, a lot of publication the last 4 or 5 years using a Williams fundamental limit to solve various types of problems in data-driven fashion. And I'll give you the gist of it again. Essentially, it boils down to the fact that if you take data of the system, let's say you use some kind of control, and then you use the state, you measure the state, then you have, this is x0t, that's the length of all the data that you have collected, and you also use x1, it is basically one shift of the data. So you can, x1t comes from x0, right? So it turns out that these data are related through this expression here. So you can see x1t, you know, this and this, you know, A and B typically you don't know, but there is this relationship that connects the two. And you can use this relationship to work with x1t, u, and x0, so the B and A. That's the key idea. So if you assume a control law of this form, and then under persistence of excitation, which is needed for this problem, essentially, you can show that any controller K can be reparameterized by another matrix G in terms of the data of the problem. Okay, that's the main idea, and they use this idea to solve different types of problems. And we do the same thing for covariance steering. So I'm gonna show you here, there are two parts here. There is a mean steering, how you control the mean, and how you control the covariance. The mean turns out to be this problem. As you can see, if I write the mean equation only in terms of the data, it looks like this. Okay, you mean mk plus 1 is equal just the data, and then is controlled only by the feed-forward term. And it turns out this is kind of it's equivalent to this problem where you solve A hat and B hat by solving this problem. So essentially, actually turns out, to make a long story short, for the mean steering problem, solving the problem in a data-driven fashion is almost exactly equivalent with an indirect approach, because you could actually alternatively solve some A hat and B hat and plug it in there and solve that problem. So it is actually equivalent. But the more interesting to us is the covariance steering problem, where now you want to find K that solves this problem. And again, we're going to do a similar trick. So you're going to rewrite the covariance equation like this, and then you reparameterize using this parameterization in terms of the data of the problem. It turns out that this equation looks like this. So you can see x1 now appears as part of the problem. These are your data. And then you want to simplify this. You do this transformation of variables. Sigma inverse shows up again, and you do the same trick. You use this slack variable, and then you make it greater than equal to 0. You do the relaxation, and you get through Schur complement, you get an LMI. But it does not be lossless in this case, but it works pretty well in practice. All right, but it turns out to be a convex optimization problem. So what you do with you have noisy data. I'm not going to go through that. You can look at this paper that will appear in Automatica soon. If you have noisy data, essentially you have a noise in this equation. That means that you collected a noise in your data. And the problem is solvable as long as you can figure out what the noise is, because if you know the noise, you can subtract the noise and you go back to the previous problem. So there is a way to estimate noise using maximum likelihood estimation. Again, the details are in the paper, but your estimate is not exact, obviously. You're just an estimate of the noise. It turns out that you also get an estimate of the error of the noise, and it turns out to have a bound like this. The probability of your estimation error belongs to some set is greater than some. So you have some bound of that form, and it turns out that first, interestingly enough, this bound is actually independent of t if the data is persistently exciting, which is kind of interesting. We're using these results essentially in this bound. So you use robust control techniques. Now, it's not really robust control techniques, but basically tells you if you have some uncertainty in some bound, then you can do some controller. Of course, here's a probabilistic bound. So you use that under the agreement, silent agreement that everything you prove now is going to be with high probability. So you can use robust control techniques for certain uncertainty belongs to a certain bound, but then, okay, all the results you're going to get is going to be with high probability, right? So then you do a robust data-driven mean steering. So essentially it turns out to be able to try to solve this problem where A is the estimate and delta A and delta B are some kind of bounds that you have. With high probability, you have this bound, and then the robust control, the robust data-driven covariance steering turns out to be a problem of some robust LMI of that nature, where again, this is given by this bound with some high probability. So we use system-level synthesis to solve the robust data-driven problem, and we used robust LMI techniques to solve that problem. So let me show you, I guess, the results. So here is two examples. So here what I'm doing two things. So for the first problem here, I have a bunch of data and I take different realizations of different data. And for different realization, I construct a new A hat and B hat, and then I run it against the actual system. So you see that the controller, if you don't use a technique, you just do regular data-driven mean steering, you have big dispersion. But if you use the robust way that I just explained, then you see the mean is really concentrated around, around the area, the correct one. Most interestingly enough, if you want to do both covariance and mean steering, here's an example that you try to steer the mean, assuming that this is actually the certainty equivalence. So you don't really take into consideration the noise. You assume that, okay, the estimated A hat and B hat are the correct one. Then you implement it in the real system and you see, you don't match the mean or the covariance. If you do robust covariance, but you don't control the mean, then you see that you have a better control of the covariance. But of course, because the mean is moving around, then you have this cloud of possible terminal states that you can end up. And of course, if you do control both the mean robustly and the covariance, you see a pretty nice control. All right, so let me skip this a little bit because I would like to go to the applications that are more interesting. So this is the idea here is that you can do the same thing in a distributionally robust manner, in the sense that in this covariance steering, you assume that the noise is coming from some distribution and that's entering the system. For example, the noise that hits the system comes from some zero mean with some given covariance. But how do you know that the noise in the real system is a Gaussian, especially with this mean and covariance? Or how do you know if it's even Gaussian? Typically, may not be even Gaussian. So there is a way to characterize all distributions that are close to your nominal using these Weissenstein ambiguity sets, which is essentially using essentially, you say that I'm going to characterize all disturbances that are not far away from me, okay, in some ball of radius epsilon. How do you measure distances? Well, it turns out that the right way of measuring distances between distributions is exactly this, which is nothing more than the solution to the optimal mass transport that I showed you earlier. Anyway, there is a way to compute that, and the only thing to remember is that there is a way to characterize how one distribution is far away from the other, and you can use these types of results to get bounds about how the distribution, the uncertainty of the distribution, so it's uncertainty on the uncertainty, if you think about it, propagates with time. Okay, I'm going to skip that. There is a few things here. The main thing is that we're using this result by Doppler's group at ETH that basically tells you how to propagate ambiguity sets via some linear transformation. Nice result, which allows you to propagate these sets along with some result on how to take care of distributionally robust constraints. We use conditional value at risk here for this, and we need to compute things like this. So these results allow us to propagate and find sigma k, right? That's the ambiguity set that the distribution of the state at time k belongs to. But even that is not easy to solve. So we do one more trick, and then from the distribution robust Western sets, we go to some Gebrich ambiguity sets that are a little bit more conservative, but are easier to handle because it's difficult to compute these Wasserstein distances in general. So the Gebrich ambiguity set essentially measures distributions through their first moments and is easy to compute. And for Gaussian is exact the Wasserstein, but in general it's not. But at least it's computable. I'm just going to show you some results. So here is an example where you have here's a regular covariance steering where you have a nominal disturbance, okay, and you see here it actually no surprises. It matches the states. Here are the constraints here, this corridor. Both of them match, but it turns out actually the distribution robust is a little bit more conservative. It's trying to stay away from the constraints. No surprises here. Then, all right, that's no surprise. Now here, let's say we change now, and instead of the assumed distribution of the noise, now we hit it with another, we call it the extreme Gaussian distribution. That's the Gaussian distribution, which is at the edge of this distributionally robust ball, so epsilon. So we're taking a Gaussian, which is as far away as possible, and still within the set that we have assumed, and we hit the system with this and see what happens. So you see now the covariance steering you have this red, I don't know if you can see this red trajectory, it means they violated the constraints. So you're still violating the constraints because it's not designed to handle, Gaussians except the one that it assumed it was the correct one, where the distribution robust, you see it's much, much better. And then for even worse, you can hit it with some non-Gaussian distribution as long as it's with this distributionally robust this Wasserstein set, and you can see again you have violations because it was not designed for non-Gaussian distributions. The regular covariance steering were here. The distributionally robust works much better. All right, some applications. I have about, I guess, 20 minutes, 15-20 minutes. Okay, is that okay, Naira? All right, okay. So hopefully I'll be able to give you I like to give a potpourri of 3 different examples, one from control, one from robotics, and one from generative AI. So I may skip one because I really ran out of time, but one of the first examples we used was stochastic MPC. As you know, in stochastic MPC, in general MPC, you solve a problem in chunks, and you reparameterize and you reparameterize and you reparameterize, right? So you reoptimize and you reoptimize and you reoptimize, and you don't look at the whole horizon. You just look only for a finite horizon. And every time you look at the finite horizon, things can happen because you throw away stuff and you don't know what happens after the horizon. So it may happen that by doing this successive optimization, the problem may not actually converge. This is a very well-known problem in MPC in general, and there are people who have been working on this side to solve this problem. And the classical way of solving is to add a constraint at the end of the horizon such that you guarantee that if your trajectory ended in this set, then the problem will have a solution. This is called recursive feasibility for those of you who know about this. And this is the main thing about this type of MPC problem, how you guarantee recursive feasibility, how you gonna guarantee that every instant of time, when you solve this problem, you're gonna have a solution. You don't want to fly an aircraft, right, and suddenly MPC comes back and says, sorry, I cannot find a solution, right? So, so in order to guarantee this recursive feasibility, people add these sets. Now, if you have a stochastic version of MPC where you have noise, then you have to guarantee that the trajectories will enter that set. So this is the reason most people who have been using stochastic MPC for many years, although they may have stochasticity, they assume the stochasticity with an unbounded set, because then you have a bounded set here, you can propagate it, you can figure out that the set enters in this final region. But if you have unbounded noise, however, like Gaussian, with an infinite support, there is a non-zero probability that any set will leave, any trajectory will leave some set, or there is a non-zero probability that some trajectory rather will leave any set, any bounded set. So this is a problem. What we did is, change this type of constraints with covariance constraints, because you need to have to guarantee that at the end of the trajectory things will work out. So it's exactly the technique you want to control the trajectories at the end. So essentially you have a control of the mean as usually, but then you have an extra constraint that control the covariance. All right, I'm not gonna skip to that. There is an interesting also trick here that we parameterize the control using an interesting parameterization. You can read the paper if you're interested in. We implemented that with this Autorally platform that we have, and it works, much better. And that's why a good example here, because really this system is really stochastic. I mean, there's no way you can model all the bumps and everything on the ground. So this is really a stochastic system. So it was turned out to be a very nice implementation of this technique. We also did a little bit some work with Evangelos Theodorou here in our group, in our department. That was the MPPI. He developed this nice technique and works nicely for many applications. Very simple, and I think the beauty is in its simplicity, but has some issues for certain types of problems if you have uncertainties and so on and so forth. Roughly speaking, is that you inject noise to do some kind of exploration, but if you inject too much noise, you start looking at places that you'll never encounter. If you put little noise, you don't explore much. So what you like to do is to have, roughly speaking, to modulate the amount of noise you inject into the system to do the exploration to generate these trajectories. If you know about MPPI, that will be clear. If you don't, then that what I'm saying may not make too much sense for you. But essentially, you explore trajectories over a certain horizon, and then you take some kind of average. So the type of exploration makes a big difference about what kind of trajectory you want. So that's the idea, and we like to make sure that we explore much, but at the end of the horizon, we bring the trajectories down back, so we don't explore things that we don't want to explore. So here is we have a simulation environment. Here is on the left is a standard MPPI. The right is covariance control MPPI. These are fandom obstacles, and you can see just basically look at this table that we can go much faster. The lap time has been decreased from 6 to 4, and we have much higher success rate. So we implemented that on our little system. So it's pretty competitive. I mean, it's difficult to beat. Definitely not a novice human, even we don't have an expert human, but it's going pretty aggressively. It's pretty difficult to beat. All right, I'm going to skip that. That has to do with belief mapping, belief roadmaps. All right, let me go back to Schrödinger bridges since I have only a few minutes left. So remember that the Fermat's theorem had this very interesting result that basically told you that a Schrödinger bridge is an average of Brownian bridges. Okay, and our what the objective here is that we have this technique that we can use, we can solve exactly the problem from a Gaussian distribution to a Gaussian distribution. But most systems, the initial is not Gaussian, it could be anything, right? So is it possible to extend our work on to something else that captures Gaussians? That's what motivated this problem. Now, this result by Fulmer was recently by the machine learning community was extended rather to this result that basically says, well, you don't really have to have the optimal mass transfer. You can take any coupling Q, and then if you have solved the problem between the beginning and at the end, and you have any coupling, then you can take the average of those and you can construct the solution between any point and any other point. Again, it's kind of the same idea that you can have point-to-point open loop solutions if you want, and then you can mix them and you can get some kind of feedback solution from any point to any point. Okay, and not only you get that's another interesting thing. Not only you get the corresponding density, you also get the corresponding control. So it's a control that will generate this density. Okay, so there is an explicit formula that tells you, which is very, very cool actually, right? So if I give you a bunch of controllers, this is UT that takes you from a single point to another single point, and I know from any point to any point how to solve this problem, and then I can mix them, then I have a way to tell you, then I can solve, you know, the distribution problem. So, right, so that's the result. And having this, we said, well, we can maybe use this idea to extend the Fulmer's result, which is a mixture of Brownian bridges, to mixture of this, you know, covariance to covariance bridges. So essentially, we want to solve this type of problem. I have a linear system, but now I want to go from a mixture of Gaussian to a mixture of Gaussian. All right, so that's much more interesting and much more general because now you start capturing more general distributions. And what we hope to do is that since I know exactly how to solve from one Gaussian to one Gaussian, maybe I can mix them somehow, similarly to the previous result, to get as a result for a Gaussian to Gaussian mixture. And that turns out to be possible. So there is a way to compute the so-called the transport plan that basically in this scenario tells you which Gaussian goes with which Gaussian, or which part of the Gaussian goes with who goes where, roughly speaking. Not exactly, we get an upper bound. We actually recently submitted a paper that shows that there is a gap. There's no way you can get exactly, at least with this formulation. But in any way, it works well. And it turns out that you can get the corresponding policy, okay, and the corresponding probability flow. So if you know lambda ij, this tells you which mode of the initial Gaussian mixture goes with which mode to the final Gaussian mixture, or which percentages, if you wish, then you can mix the solutions. UTIJ is the solution from the covariance steering from mode I to mode J, which we have, okay? Then you can mix them and you can get the solution to the Gaussian mixture from Gaussian mixture. All right, so here's an example all right, from that shows that we can go from one shape to another shape. Here's a more or less traditional example that shows that we can do generative AI using control techniques. So let's say that you want to solve the problem of image to image translation. So think about you have a distribution of images of men, and you want to generate a new image in the space of faces of women, and you want to find the sample of in the space of women that is more closely as possible to one of the images, right? So this is a distribution problem that you want to take this distribution, you want to shape it to this distribution through some system of that form. All right, so ideally, okay, we can use this this technique, but of course, there is no way you can put a mixture of Gaussians here and a mixture of Gaussians here. These are very high dimensional spaces. So instead, we do that in the latent space. So we have an encoder that takes the latent space of the original distribution. Then we do the mixture of Gaussian to mixture of Gaussian in the latent space. We call it the latent Schrödinger bridge. and then you decode and they can generate images. Let's see how it works. So here's our results. GMFLOW is our technique. This is the original image, and then we want to, this is actually adult to child translation. So we get this original image, we generate this image. This is a woman, generate this image. This is the original, generate this, etc. So you can see this is our technique. Light SB is the state of the art, I would say, in this type of problem. Light starts it's a light speed Schrödinger bridge. Most interestingly, in terms of beyond just visually, that these are very high quality images generated. Look at this. Look at the scores. These are scores that this community has been using to test how good the generation of image is. This is the state of the art, and we are 50% better in FID scores, and I don't know, several, 5-6 times better in terms of this type of score. So we're not interesting, or not only that, there's no neural network training here. It's just basically solving a convex optimization problem using control techniques. So it's I think it's kind of nice to see how you can use control techniques to solve this type of problems. Last but not least, we have extended this result. The way that the problem that you can shape distribution can be used not only stochastic systems, but can be used in systems when you have large populations of agents. I mean, if you have large populations of agents, you can think of them as particles in a bigger system. So it's just, and instead of looking at each agent, you just look at the distribution, the macroscopic properties of the system. So this is an application to mean field control. So if you have a bunch of agents that interact with each other, it is a continuous time here. So if you have a differential equation, stochastic differential equation for each agent I depends on some potential term that interacts with its own, and then some potential term that tells you how it interacts with its neighbors. Then if you take a large number of agents, it turns out that this equation can be characterized at the limit by this equation here. This is the type of equation that are called Makin-Vlasov SDEs, because it's a regular SDE, but you can see it has this extra term here that depends on the mean, all right, or the distribution of the mean, or in this case of the mean, or in some more general forms of the distribution of the system. So every representative agent, right, as t goes to infinity, as n goes to infinity, depends also on some macroscopic properties. All right, so you can write down the equation. You have the problem that looks like this. You want to solve for any initial distribution to any final distribution. Too difficult for us, so we skip and you say, okay, instead of row 0 and row 1, we're going to use mixture of Gaussians. So we can solve this problem if this term did not exist, but unfortunately it does exist. However, we show that in these terms, it turns out that the error between x and x hat, which call x tilde, turns out to be 0. So if you write down the equation, it turns out, roughly speaking, that this term does not. You can handle it. Actually, it doesn't bother you. So, and you can solve problems, like this from where I say here, from 3 Gaussian mixtures to 10 Gaussian mixtures. Think of it as like a bunch of particles or agents that they move. In this scenario, they can go through some obstacles and things like that. All right. So takeaways. So I hope I told you that. I hope I convinced you that directly controlling distributions of trajectories leads to performance guarantees, because you can really tell exactly how the distribution is going to be at the end of the horizon. This introduces what we call as uncertainty synthesis. This is a term that was coined by Yongxin Chen, and I like it. Basically, and instead of controlling systems with uncertainty, which is the classical way of looking at things, here we're directly control the uncertainty. It's more a directly control the uncertainty as opposed to systems with uncertainty. There are many applications. I showed you a few to motivate the discussion on pinpoint landing, swarms at the end. There is results on nuclear magnetic resonance. I showed you a couple of ideas or a couple of applications on generative AI, but there are many others. I mean, everywhere you look, you see problems that have to do with controlling some distribution or one way or another. So there are many problems that still we can work on. I believe that in linear dynamics with Gaussian distributions, well, it's pretty well understood, the theory, but there's a lot of stuff that we can still do, non-linear dynamics, non-Gaussian, hybrid dynamic, controllability questions. We have partial answers to this, free final time problems, etc. These are nasty because you have to deal with stopping criteria and a bunch of applications as well. Again, there are many problems to look at if you're interested in this area. Right, I'll try to stop here, and I'd like to thank, of course, all the people who did the work, all my postdocs and students. This is several years work, and my colleagues here at Georgia Tech and elsewhere. So I'll stop here, and I'll be happy if we have time to take a couple of questions.
Thank you, Panos. It was great. Let's see what questions come up from our group. They are usually active with questions.
Yeah, hey, Dr. Tsiotras, really good, very interesting work. I have a question. You talked at the end about basically controlling mixtures of Gaussians, and I'm wondering if there's a construction problem, right? Can I, given a distribution, you know, kind of like a Fourier series where I can reconstruct a function, can I reconstruct any arbitrary distribution as a mixture of Gaussians? I guess I'm asking.
Yeah, there is a theorem that says mixture of Gaussians. There always exists a mixture of Gaussians model that arbitrarily approximates arbitrarily close.
Yeah, arbitrarily close.
Yeah. The question is how many modes you need, right? So
right.
So after a while, it could become pretty difficult. But yeah, these are very well established problems. That's the idea, that if you do mixture of Gaussians, essentially you capture a lot of distributions, at least if you don't care how many modes you're going to use. Now, in reality, after using more than 12, 13, 50, whatever it is, becomes a little bit complicated, especially if you want to do it from 50 to 50, then you have to, solve this problem. It's kind of a combinatorial problem, although it's linear, as we showed, there's a linear problem. But yeah, to make a long story short, yes, that's the idea. That's why we use mixture of Gaussians, because you can you can approximate arbitrary distributions as well as you want. Okay, the price to pay is how many modes you're willing to include in your mixture. Yeah.
In your opinion, let's say you start out with an unknown distribution, and you want to drive to some distribution. Do you feel that there's a kind of a, so you've shown the control using the GMMs. Do you feel there's a process to learn? Like, can you learn the mixtures that would drive you to some? Yeah. Okay.
Of course. Yeah, that's exactly what we did. For example, in the image space, right? So imagine you have this image. You want to transfer the image to image space, right? So it's a very high dimensional space, right? I don't know, it's like a zillions and then we map this to the latent space. So in the latent space, there is some distribution. I have no idea what this distribution looks like. But we have samples, right? We have samples from this of these images. And then using standard techniques, very standard techniques, how to map using maximum likelihood estimation to map any distribution to can find Python or MATLAB code, and you can create this mixture of Gaussian. So if you have this mixture of Gaussian, then we take it from there. Does that make sense?
Okay.
Yeah.
No, perfect. Thank you.
Yeah.
Good stuff.
Yeah. It's a very well studied problem, how to fit a mixture of Gaussian to any distribution. Yeah.
Aditya, go ahead. So we have two more people from the group, then I'll go to Pan. Aditya, go ahead.
Hi, Panos. Thank you so much for the lovely presentation. I just have a quick question regarding the distributionally robust covariance terrain, especially the radius of the ambiguity set. How do you decide on that? How is it figured?
Well, yeah, that's a good question. I mean, if you have some prior information, then you, well, oops, well, sorry, well, let's see here. So there are several parameters here, right? So the first one is, okay, this epsilon parameter, and then there is this delta parameter. This epsilon parameter basically tells you, okay, if you know your noise and you're not confident about where the noise is, maybe it's Gaussian, but basically you have to have some idea, right? So, and then there is the other parameter that, I don't know, it's not here somewhere, basically tells you that, here it is, that I would like to steer the terminal ambiguity set inside another ambiguity set. In the terminal, again, I don't know, this is my nominal, but at the end of the horizon, it's gonna be impossible to hit this nominal because have uncertainty where I started, right? So the only thing you can expect is at the end there is an ambiguity where you're going to end up at the end, but this has to be inside this ambiguity set at the end around the nominal that you have should be inside delta n, right? So this delta that you refer to it's in the paper. There is a way to compute it. Now, it may happen that the problem may become infeasible if you are very strict, right? So that's kind of there is a relationship there that it comes with the specifications of the problem, and then I'm assuming here that there is a way that you can compute. There is some bounds that you can put there, and then that's how it works. So if your delta is very strict, I mean, you're gonna have the problem will give you an infeasibility. So forgot to mention, maybe it was obvious or maybe it was not obvious, all these things that we do, and then we relax these constraints. There's a bunch of steps that I skipped here. There is also distribution robust objective function. There's a way to do that, but all these things turns out to be a convex problem. Okay, so everything with the solution we get solve a convex problem. Now, it may happen and say, oh, sorry, I couldn't find a solution, right? So that means it doesn't mean the original problem was unsolvable, not necessarily, because you have done some kind of conservative approximation, right? But that's a price to pay for efficiency. Does it make sense?
Okay. Thank you so much.
Yeah.
Yes.
Okay.
Thank you.
Yeah.
Pan, go ahead. Pan, go ahead before we.
Oh, sure. Yeah, Dr. Tsiotras. Yeah, thank you for your talk. I have maybe two quick questions. First, so in this covariance steering controllers, what is the typical form of the controller? Is it still like the standard feedback controller, like U equal to minus kx, something like that?
Yeah. There are in the literature, there are several variations, but turns out most of them are equivalent. It turns out that you can also use disturbance feedback or disturbance history feedback, but that turns out all of them are kind of equivalent. Now, in the paper that I showed you, at least when you have no constraints, right? It turns out this is the optimal one. It's kx minus r. Where was that at the beginning when I tell you the basic result, right? Oops. Right. So it turns out the optimal control is of the form kx plus u. So, so yeah, if you lose linear controllers, at least for the standard problem, it is optimal. In general, I don't think there are people have shown this. I mean, if you, let's say you change the problem, you have constraints or you have output feedback or whatever. Well, I don't show any proofs, but you start from that you start from this, and I think it works. Yeah, so makes sense.
Yeah, so that basically means that for online implementation, its computational cost actually is not high it's not higher than the standard controller.
Yeah.
Okay.
I mean, it is. Yeah, correct. I mean, it's a convex problem. How big this problem is. I mean, whether you can solve it online or not, that will be right. You have a convex problem, right? So now the question is that can you solve that on the fly? I mean, because it's convex doesn't mean it's fast, right? It depends on how you implement it. But at least you you have an idea what you're looking for. And the nice thing here is that if you solve this convex problem, you get exactly the solution. If you have a good, if you have very often people, what they do, well, I don't know. I mean, just getting the discussion here is some people you may be able to keep the K constant if you want to. That kind of goes like a tube type of approach as opposed to controlling directly, especially in MPC, because I think you mentioned about MPC, right?
Actually, I wanted to ask about the covariance steering version of MPC. How is the computational cost compared to standard MPC?
Oh, it's heavier because you have to have extra stuff to take care of, right? But it's a convex problem the way we formulate it, but it is a bit heavier.
I see. So for this convex problem, do we need to solve it online, or we just need to solve it offline once?
No, typically you want to solve it online, but you can play tricks because it's not necessarily true. How often you need, I mean, ideally you want to solve K because a time varying system, right? A discrete time varying system. If it's not time varying, that's better. But if it's a time varying system, the A matrices and the B matrices are changing. So you have to adapt. K has to be changed. So you have to solve it on the fly typically. But if you think about it, do you really need to update your K matrix at the rate at which your nominal is updated? Probably not. So you can play tricks and you can you can update the K matrix only every 10 steps or something like that. So you have 10 steps to solve this convex problem. You know what I mean? Although ideally you'd like to solve it at every instant of time, you get the best performance. It turns out that you can solve it, every 10 steps or something. It should be okay. And you keep the K constant for 10 steps. I mean, think of it like that. So yeah, if you have the computational resources, you should solve it on the fly. If you don't, you have to play some tricks, some heuristics to update not as fast.
I see. That makes sense. Thank you very much.
Yeah.
Shubhra, go ahead. Panos, sorry, it goes a bit overboard.
No, that's fine.
Shubhra,
That's fine. I
go
don't have any.
Okay.
My next meeting is.
So I have a very high-level question. Let's say that I want to train some high-dimensional model like image-to-image translation or some generative world model, which are basically high-dimensional dynamics prediction model. And I don't know how many layers or what are the network complexities that I need for that particular task. And I also don't have any idea before training that what will be the layer-wise covariance or guarantees, right? Now, can I do something like this and use your covariance steering somehow that, let's say I start with some predefined layers, which is a lower number of n layers, and I know my input distribution and some desired output distribution. And I start training for some time. And after some time, I see that, okay, n number of layers is not really sufficient for my task. And then I keep progressively adding more and more layers until the point I reach the desired covariance output layer, right? And along this training process, I actually have some sort of layer-wise guarantee based on some kind of covariance estimate. People, when they're training these deep learning models, they usually use normalization for each layer, which is like batch normalization. They estimate their moments and keep normalizing their output. But there is no kind of guarantee that your estimate will give you some, there is no bound or probabilistic safety guarantee in each layer, right? So can we use some kind of covariance steering from some of your method to do that?
Well, that's okay. There's a lot of to unpack here. There's a lot of ideas. We have done a few things. Some of them are not published, but let me tell you a couple of things. So if you discuss about neural networks, right? So neural networks are nonlinear. You have a nonlinearity in there, right? So you cannot use directly this approach that assumes a linear system directly on that network because at every layer you have a saturation function or what have you that destroys the theory, so to speak. Okay. Now, having said that, let me say there is some work that we did. If you look at this I invite you to look at this problem, non-Gaussian, and there is a follow-up that we're using this idea. So it turns out the following. Here's an interesting result that may be related to what you just said. If you take a neural network that has linear units plus, and then let's say the nonlinearity is our RLU activation function, which is okay, fair enough. RLU is pretty good, right? So without loss of generalities, have a neural network with RLU activation function, which is basically a max operator, right? It turns out that you need to do two things, right? One is to propagate through the linear system, which is fine, and then you have to propagate the distribution through this ReLU function, and this is a kind of nonlinear operation. If you, however, look at the characteristic function of the distribution and not the distribution itself, it turns out that there's a closed form expression how to go through the max operator. So I invite you to look at this. I'm going to send that to you. We looked at this problem where you have a neural network where you want to propagate the distribution through the neural network. We have a couple of papers, but we do it in terms of the characteristic function. It turns out to be the dual space. It turns out to be more tractable because there is a theorem that allows you to pass a characteristic function through a max operator using Hilbert transform. I can send you the reference if you're interested in. I think maybe that will answer your question. I'm not sure. But in general, you cannot just use it out of the box for a neural network because you have these nonlinearities, right? This is a linear theory so far. We have applied to nonlinear systems using successive linearization of successive convexification, but you cannot just pass it through the neural network, at least the way this is formulated right now.
I see.
Yeah. But if you send me an email,
regarding paper, there is a question in the chat regarding the latest link, the latest paper and the link to it, if it's available on archive.
Which one?
You could put, just check the chat. Michael from NASA is asking for the latest paper.
Several paper. Is the latest paper? Which latest? I mean, most of them. Yeah, I think most of the papers should be on archive. Yeah, most of the papers, even the ones that are to appear in automatic. I think this one, yes, it's on archive. All of them should be on archive. Yeah.
Okay, great. Thank you.
And Petros has a question, and you will send us the slides, so we post it with this video. Petros, go ahead with your question.
Yes, hi Pano, very exciting presentation, very nice.
Thanks a lot. Thanks.
My camera is broken, so I sorry for not showing.
That's okay. I know how you look like.
No, I'm looking better now.
Okay.
Anyway,
actually, a minute ago your face showed up on the camera.
Yeah, but now it got stuck, and it will take several minutes to get it back. Anyway. So my only question, I guess, is the following. So all of these developments, which are really very interesting and exciting, are based on a finite horizon,
right? Yes.
Right. So do you envision this kind of work talking more about, I don't know, an infinite horizon, including some more stability, closed loop stability type of things?
Yeah. Actually, the infinite horizon problem was solved before. I didn't have the. If you were at my plenary at ACC, I gave a talk about the covariance steering. It was named after covariance controls. Bob Skelton looked at this problem in the 80s, right? So he looked at the infinite horizon problem, where he said, is it possible to maintain this covariance at the infinite horizon, right? So then he liked this assignability type of problem. So yeah, if you're interested in, and there are questions about stability and all that. So if you're interested for the infinite horizon problem, look under covariance control rather than covariance steering. That's the way to distinguish covariance control, and look at Skelton did a lot of work on that area. Yeah.
Yeah, but in the context of, this modern world applications, do you see that having any use, or is it more, it's kind of a...
It's a good question. I haven't looked at the infinite horizon so much because we're just focusing on the finite horizon type of problem, but not at the regulation type of what Skelton did. But I don't know. Yeah. Yeah, I don't know. I mean, maybe worth it. There may be problems to go back and look again. We discussed a little bit with Trifon, and I think Trifon has started. He had a paper that looked at in one of his papers. There was a part 3, I believe, or these two parts. The part 3, I think, he looked at or part 2, I don't know where, he looked at what happens at the infinite horizon. You cannot, I mean, the theory says that you can hit that particular covariance. It doesn't say that you can stay at this covariance. Just say, okay, you hit this covariance, the game is over. You stop the experiment, right? Whether you can maintain this covariance or not, that's the question you're asking, right? Can you maintain it? The answer is typically no, you cannot. There are algebraic conditions that tells you whether this covariance that you hit, you can maintain this forever and ever, right? So these are the problems. These are algebraic conditions. You can find those. So yeah, that's my answer to that question.
Yeah. Thanks a lot.
There was another question. You said you have 2 questions?
No, just.
Okay.
So if no more questions, let's thank Panos one more time. And Panos, please email your slides and the paper links, and we will post your video of this seminar and the slides on the Aviate website. The papers I will share with our team and Michael from NASA and the NASA researchers who are on this call as well.
Okay. Thanks a lot.
Thanks
Thanks again
everyone.
for the invitation. Thanks.
Yeah, I'll look forward to your email now, Panos.
Okay,
Thanks.
yeah.
Bye.
Thanks.